Hey folks, welcome to video 2 for 4.1 or video B. We're going to explore impulse and change momentum. This is the first confusing part of the unit where we talk about basically an extension or another way to think about Newton's second law. So let's get started. We're going to start with Newton's second law and we're going to derive what impulse is. I'm going to do this from time to time because I think it's valuable to show you how many things come from Newton's second law and how all of mechanics is really based on this one equation. So net force equals mass times acceleration for any system's center of mass. And our definition of acceleration is it is the rate of change of velocity. And so if I combine those two pieces of knowledge, I can write this equation as the net force is equal to mass times the change in velocity over the change in time. So now I have net force in terms of velocity. You've done that before with like motion graphs, but you maybe haven't done it with this derivation. Okay, now if momentum is mass times velocity, then the change in momentum should be equal to mass times the change in velocity. That's a bit of a corner cutting for me, but it's true for this course. Truthfully, the change in momentum is the change in the product of mass times velocity, because objects can change their mass and change their velocity depending on what's happening to them. So like a space shuttle that's firing is losing the mass of the fuel it's ejecting and burning, and it's also increasing in velocity. So the change in momentum is due to the changes in both of those variables. For AP Physics 1, we do not explore systems where the mass is changing, so the delta goes with velocity. So I can rewrite this as the net force on a system is equal to the change in momentum divided by the change in time. This is Newton's second law written in terms of momentum, which I believe was actually the original way that Newton wrote out his second law. So net force and momentum are closely linked. Basically, what this is saying is if you apply a force to a system, its momentum will change, which makes sense. So it's establishing that the net force is equal to the rate of change in momentum. And we'll take that like one step further. I'm going to multiply both sides by delta t, and we have the net force times time equals the change in momentum. And so this sets up the idea of impulse. In order to understand this idea of impulse, we're also going to just remind ourselves that when we see a change in a variable, that's equal to final minus initial. So we're setting up this new term called impulse that has to do with how an object's momentum changes. All right. From this section, this equation is pretty relevant, and we'll come to it later in the video, actually. All right, so impulse. In different textbooks, impulse has different variables. In our textbook, it's J, and in the AP Physics 1 equation sheet, it's a capital J. Impulse is defined as the average force delivered to an object times the time over which it is exerted. Now, average force is really just there to tell you that there are constant forces and there are variable forces. And you can have an impulse that's based on a constant force, where the force is always the same number, or a changing force, but this formula requires that you then average out that force. And I'm going to show you what we mean by that later. You're never going to take an average of a set of numbers when you're doing this. All right, that is the equation for impulse, and impulse is equal to the change in momentum of a system. And we kind of see that from above, right? Force times time, we said in the previous section, was equal to the change in momentum. So that's where that definition comes from. What that means is that this variable J is the same thing as the variable delta p. So it gets its own variable. It doesn't always get its own variable in every textbook because it's just so closely linked to change in momentum that a lot of textbook authors don't feel the need to give it its own variable. Anyway, impulse is analogous to work, right? So when we talk about like work, that is like a net external force that changes energy. The way that I wrote that equation for work being a change in energy is I wrote it chronologically. The mechanical energy of a system then gets changed by the amount of work done by external forces, and that is equal to the final mechanical energy of a system. Impulse, if I did some more algebra up here with some of the equations I have, I could write the following equation. The initial momentum that is then changed by impulse is equal to the final momentum. So because work is equal to the change in mechanical energy and impulse is equal to the change in linear momentum, I can write very similar equations for both concepts. Really, they're just both extensions of Newton's second law anyway. So everything comes back to when an external force is applied to a system, its motion will change. And so Newton's second law does the same thing. All right, the last section is about graphs. At this point in the course, you start getting into like lots of different graphs and even ones that we will not talk about. You'll see them and you'll have to analyze them. So I'm going to give a little bit of an overview. Impulse, because it's average force times time, you don't always get to plug in a value for force. Sometimes the force changes. When objects collide, they deform. And so the amount of force delivered through that collision, it ramps up and then it ramps down. If you think of like a racquetball or a tennis ball, it squishes when at impact and then it like extends back up. So the impulse on a system is equal to the area under a force versus time graph. And what's really interesting is that when you do that, the math that you're doing is essentially locating the average force and then multiplying it by time. So that's our impulse with a force graph concept. Now, it's going to be important that you remember that if we change this to a graph of force versus displacement, then the area under the graph would be the work done. So that's something that we'll have to think about together later. Momentum versus time graphs are less common, but they are still part of our course. And we have already determined that the net force is the rate of change in momentum. Well, this formula is set up as rise over run. And so if I have a graph of momentum versus time, the net force is equal to the slope of a momentum versus time graph. And so this is a graph of momentum versus time. A lot of this stuff you can figure out based on what you know about physics already. But if the momentum is constant, that's a slope of 0, and that means the net force is 0. Think about that for a minute. If the momentum is constant, that means that the velocity is constant, which means that the acceleration is 0, and therefore there's a 0 net force. On the other hand, if the momentum increases linearly, that is synonymous with a positive net force. We get an increase in momentum, and so a positive net force. So there's a positive net force that causes acceleration. The velocity becomes more positive. And that's it for now.